anything else I need? Anyway, hello everybody. My
Hello.
name's Jerry.
Hello.
In case you guys haven't met
Nice
me
to
yet.
meet you.
So actually, I did invite some of the quick update. I think nobody knows yet, but Dr. Larson found me a project on protein structures prediction, and this is a viable and very active research area currently because of the work of AlphaFold in the past, well, let's say, decade.
Can you tell me like what group it is? Like who you're working with?
Yeah, I'm working with Dr. Tao of the chemistry department. Matter of fact, I did invite some of my teammates to come, but I'm only like
Dr.
familiar
Tao,
with one
you
dude.
said?
Yeah,
Okay.
I'm only familiar with one dude, and then the rest of the guys, I guess, just don't on me. Anyway, which is fine. But yeah, actually, I may send this recording over. But AlphaFold, let's say the importance. Well, okay, sorry. How much do we know about AlphaFold?
Nothing.
Not Nothing?
Much.
Okay, like just like you mean like structures of it, or just general knowledge? Do we know that this got some dude's a Nobel Prize, like half of a Nobel Prize in chemistry, right? So yeah, this is something that's very phenomenal, extremely phenomenal, let's say, in the chemistry field, and that's. How do I flip? What the? Sorry. Computer science majors. So there is a theory called unified field theory, or the theory of everything, which is a somewhat philosophical, I guess. It's more of physics. I think physicists talk about this the most, but it's a Lagrangian master equation that encapsulates gravitational, electromagnetic, weak and strong nuclear forces, and of particle interactions. So it is the equation that solves everything. And
Crack equation.
all of the years, the theory of everything is more or less just a theory and a thought experiment. However, with the scientific discovery of the AlphaFold structure and algorithm, we're stepping towards the direction of particle interactions for the sake of unified field theory. So what particle in computational chemistry is this very complicated and specific field to chemistry that was discovered by, I can't remember the guy's name, Max von Laue back in 1912. What he did is shoot a ray of X-ray through a crystal, and then he discovered that the X-ray can be diffracted by these crystals, suggesting that there is a subtle but very regular structures within these crystals. So ever since that, humans have been trying to discover and map out the structures of various elements and element structures. So all the way we can see from like 1980s all the way to 2010, humans have mapped out around 140,000 protein structures. Protein specifically because it's the most relevant particular structures that we need in terms of chemistry, biology, and let's say ecology. However, with the invention of AlphaFold, Google blew everybody out of the water. Right now we're standing around 200 million protein structures solved, which is quite phenomenal. So, what is a protein? Well, protein is, this, whatever you just ate in your tacos. But basically, proteins is kind of the pseudonym for amino acids. What it essentially is a series of atoms. Either it is a carboxyl group or a amine group that forms together via bonds that forms a particular structure. And there are 20 kinds of amino acids. And all of these amino acids essentially are these groups combined together. And the most common atoms that compose these amino acids are carbon, hydrogen, oxygen, and nitrogen atoms. Levinthal's paradox. Basically, the concept of there are a very large of degree of freedoms within our polypeptide chain. So you can think, peptide is basically a protein structure that will build out to the entire protein. But peptides, I believe peptides are the parts that are free to move. And this is why I'm dreading that my lab partner from the chemistry lab isn't here, because I'm not a chemist, guys. I do not major in chemistry. By the way, is anything that is coming out of my mouth even making sense? Right? We're good?
Makes some sense.
Okay.
I was going to ask, what is the difference between a good protein and a bad protein for their structure difference?
What do you mean a bad protein?
Like they always talk like those I'm not sure if they're real scientists or fake scientists, online they always talk about this beef is good protein and then some other fast food is bad protein. So what is the difference for their structure?
Anyway,
That's different type of protein.
so the reason why solving the structure of proteins is very immensely difficult is that when we look at these different protein groups, these 20 different kinds of amino acids, and there are multiple. There are basically 4 levels of structure for every single protein. The complexity comes from the peptide structure, because in order for the protein to form, in order for the protein, it naturally happens. So let's say in the natural world, when certain atoms are combined together, it will automatically fold to in accordance of its own sequence, as long as we're in its appropriate temperature and the solvent environment. The reason why they do that is because of the covalence and the hydrogen bonds that bonds these groups of amino acids together, forming what we know as, let's say a beta sheet or a helix sheet. Or a alpha helix. So beta sheet is basically protein but just flat. Alpha helix is protein but forms a spiral helix, which is why we can see sometimes in these protein structures, there are some line parts that is just straight, and then the rest of the parts are the curls. But going into the more complicated structures, we have quaternary structures. I've never said that word in my life. Quaternary structure that forms our eventual overall protein structure. Oh yes, and theoretically, if you have 100 residues, basically the residue basically residue. Yeah, residue. Residue basically means what's left in the protein. So basically, this whole protein, we have an estimate of 10 to the power of 300 degrees of freedom in this unfolded peptide chain.
Small number.
Yeah, yeah. It's not like if you compute all of this like throughout, with all of the computational power on Earth, it will take more than the age of the universe to get it out. Maybe the age of the universe times the age of the universe, whatever. Big number that I don't even know is called. So here is a computation called CASP. Basically, CASP is aimed as a competition to solve this problem. What are proteins' structures with computational power? Of course, there's always simulation. There's simulations as chemists have previously discovered that there's a computation simulation, which are just put in the physical rules of atoms and it will fold a certain way. But the problem of that is a very computationally expensive process. So we aim to predict the protein structure instead of simulating it.
Yeah.
So
I actually I went to one of the labs that did, or a lab in New York that did that.
oh really?
And they basically have, so for every atom, they predict it's an ODE that's evolving. And the step size is like 1 times 10 to the negative 8 or something. Or like negative 12. So you're
wow.
making this thing super slightly.
Yeah.
And they have a computer
Yeah.
that they made just for simulating that.
One ODE is only for one atom too, right?
It's for the entire thing that they're evolving.
Yeah, I know, but I'm saying the one single equation. So every atom combined, that's a big dynamical system.
Well, it's like the dynamical system for the single atom is based off the forces from all the other atoms. So it's
Exactly.
it's a mess to compute. And you don't even compute it accurately, because if you did that, it would be impossible.
Yeah, because
It's like good enough.
your computer have double precision.
Well, that's why they have a supercomputer to do that.
Quite exactly.
Super inefficient.
Inefficient, quite frankly, impossible to calculate. And remember, even with our current world computation power, it took scientists, let's say, around 2000. That's when computers are kind of popular, but it was still somewhat a linear growth after the invention of supercomputer. So yes, very computationally inefficient, very hard to solve, because of complex degrees of freedom. So what AlphaFold did on CASP is that they entered a competition back in 2013.
Hey, real quick. So is the task to take the 2D structure of an unfolded protein sequence and then trying to find the 3-dimensional configuration of it?
Oh, you just get a sequence. The sequence is just the chemical sequence. There's no There's no dimensionality to it. It's just it's like H2O.
Right, but
Just
it's
a
like a
sequence.
line, right? Like a smile string, is that?
I'm not familiar with the term.
It's just like a flat string of...
Well, yeah. Of course, you don't have to do that. You don't have to start flat. That's just how most of the
but I'm asking what's the task? Is the task to try to predict its 3-dimensional structure?
Yeah.
Right, okay.
So
Isn't
yeah.
a small string 3D?
Hmm?
Isn't a small string 3D?
No.
If you decode it into a molecule?
No,
Wait, I think you're
literally.
right. I think a smile string is... it
I
does have
think that does have
coordinate
3-dimensional information.
Yeah, that's not what I meant. I meant
Okay.
a completely flat, just a string.
Yeah, so you just get a sequence.
That's
And-
that's the input, and then you're
Yeah.
trying to predict.
And you fold it. Yeah. So basically, your algorithm need to fold the protein and then output this 3D structure. That is ultimately what we want. The 3D structure of the protein.
Sequence of amino acids.
Yeah. Yeah, basically. So, what AlphaFold eventually accomplished is that in CASP 13 is that they blew all the teams out of water. As you can see, there's, I think the good cutoff is like 0.7 is like okay, pretty good, and 0.9 is like you solved it. The rest of the accuracy is like negligible, and it's not really doesn't really matter. So it already represents its shape. So it has like I don't know around like 20% beyond 0.7, which is pretty good compared to everybody else. As you can see from the other two graphs here, some of these sequences, it just gets a really good TM score on that. Oh yeah, and TM score is basically the accuracy score for the protein.
So how do you measure the accuracy of? So just by location, like how from the like ground truths of the actual folded protein?
Great question.
I mean, if you don't know, it's fine.
Yeah, so what I learned from this, kind of going into it myself, is that there are so many things to learn, especially you're a computer scientist and you're trying to go into a field where the data is not very native to your area of study. You gotta basically learn chemistry from scratch. And that's why I really insisted to present this today, because of questions like this. So I know what I don't know, because I don't know what I don't know.
I would assume it's some version of that, right?
Yeah.
Yeah.
Probably not
So-
locational, probably, because it's invariant to location and rotation,
But relative positioning.
compared to the rest.
Yeah. I
Yeah,
guess.
yeah, probably.
Yeah.
Well, I would imagine it would be some, like, it would have to capture local and global information. That's like difficult to encode. I don't know how they would do that. I don't know.
Should I pull up this formula so we're not guessing? I mean,
Yeah.
it's just a one web search away. Yeah.
No, well, they said like accuracy. It's the
No,
meta.
the x-axis is 90% accuracy.
Yeah. TM is the accuracy, right?
Yeah.
And what's the
what's
y?
happening?
Oh yeah.
That's the okay. The FM plus like FM over TVM is basically like the you can think of it like the complexity of the protein essentially. I think, cause like cause like that's like the domain count as like
Okay.
the like having a sorry, I'm looking up the TM score here. Okay, let's see if this is at all good here. Can I put it here? No. Yeah, TM score is basically max of
One
one.
showed that formula. Should.
That is, yeah, you're right. That is
Late
amazing.
tech.
Yeah, why do we? I love how Google just don't tell you what you need
Just go
anymore.
to the images.
Like
Yeah,
yeah, that's
the
true.
images.
Like what did you
Oh,
do?
like that crap. That's
This
great.
guy. All right, that's way better, right?
Hold up. Yeah, there we go.
Boom.
There we go.
Okay, TM score is the max of 1 over. Wait, what's max? There's only one term.
Oh, it's
What? Am I missing something here, guys?
Maybe open the Wikipedia page and maybe it'll say.
Oh yeah, this is Wikipedia.
Is it maximizing?
Yeah, what the what?
No,
Oh yeah,
Max,
maybe.
Max
maybe
my
it is.
homie. Max my buddy.
Okay.
My friend Max.
Between two protein structures is defined by this, where all targets length. Okay, so length of the target, common, then the target squared. So
Why is there a max?
I am so lost.
You can max it out.
Maybe the brackets mean something else.
Maybe.
Maybe the brackets mean something specific and it's like a list.
But it's not even saying that.
The maximum is taken over all possible.
Oh, I think it's
stuff.
like.
It says the max is taken over all possible structure superpositions.
Where do you see that?
The last line of the first paragraph
Yeah.
of the model template.
Oh. Okay.
So it seems like they basically have a template,
hmm
and I guess if it's a probabilistic prediction.
No, I mean no. This is just the distance, right? Distance and then the length of the target.
Yeah, but are they themselves probabilistic?
Distance?
What's L common? L common is
The length of the there are two, right? Yeah.
So well, we have
Well,
target,
common
which
is the number of residues that appear in both the template and the target structure. So there's a template structure, there's a target structure, and then
There's
those
the
two
ground truth.
interact at what?
Yeah, there's the ground truth structure.
Yeah. So yeah, there is a that's the common, right?
Yeah.
So in its folding, it's comparing the target and then the common here.
So it's basically the sum of the distances.
So
And so you're basically taking the worst one. So you're summing the distances and you're taking the worst one. It seems like
sum. I
no,
don't
you're
think
summing
so.
the
It's just a.
inverse. You're summing the inverse.
Okay, yeah, you're summing you're summing all of the entire structure out. I think there is a
Now, if you're summing the inverse distances, then you're taking the best one. So you're
Yeah,
summing
that's-
one.
but you do sum it though, right?
Well, you're summing the inverse distances.
Yeah, yeah.
So you're basically taking the best superposition, which I'm guessing is multiple simulations.
Mm-hmm.
I'm guessing.
Okay. Yeah, that.
Unless they have like
I don't know.
I don't know.
That's something. Yeah. I'll do more research on what max exactly is.
Maybe you can ask GPT.
Yeah.
How
I mean,
paste the formula.
Yeah.
It is AI club.
it is.
That kind of stuff you could easily ask GPT.
Sometimes it's
Yeah.
just very unclear about their equations for all
If
kinds
it's
of
just
essays.
chemistry, if it's like a standard chemistry thing, pretty easy to look it up.
Yeah.
Should I do it right now?
So far, this is all
Sure.
chemistry.
Let's test out GPT.
Is the TMs for chemistry or is
That's
Well, it's not
chemistry.
machine
Yeah.
learning.
yeah, something?
Yeah.
Yeah, that's
Bioinformatics.
specific. Yeah, bio computation.
Logging.
Can you give us your username and password?
Yeah.
I would highly like your username and password. Just attach an image. It's probably easier.
At first, I thought it was like a precision recall curve or something.
That's what it's the ROC curve.
Yeah, or something.
Oh, like the blue, like the AlphaFold chart, the green and the blue lines.
Yeah.
That one.
Okay. Yes. Guess the
Formula.
formula.
Uh,
I hate how they put emojis in ChatGPT.
I felt that.
Which
I wonder
Oh,
if there's like a watermark there.
perfect.
So many people hate it too.
alignment.
It's so annoying. It's like
We want
GPT,
something that's like
shut up.
formal and professional to give us direct answers, and it's like, haha, here's some emojis. It's like, what the fuck, bro?
It gives the rocket ship emoji.
I hate the
Fire
rocket ship emoji.
I don't mind. It's cool. I like it.
You're the only
it
person.
gave you
I
the
already-
emotional
Can train
energy
I'm not a
to
hater.
comfort
You
you.
know?
I am.
I'm just not a hater.
The max
Great
refers
question.
to the
Okay, I hate that. Perplexity doesn't do that.
What?
The great question.
Okay.
That bit. That
You know, that's an insightful response.
Okay, I think I know what it is
You could get rid of
because
it, right?
because what you're outputting isn't the exact 3D structure. You're outputting the sequence of that data that represents it, represents that protein. So in the result of that, you have different superposition, right? So just means there are different superpositions, aka different alignments of either part of the amino acids that will form the. So basically, the output sequence doesn't equal to one thing. It may mean like different structures. Let's say like water molecule, right? There are two superpositions for water molecule. The H being right here, or the H being right here, but the both is like 120 degrees. So let's say there are two superpositions for that. And what you're trying to do with this max is basically all the possible superpositions based on your output, and then you're taking the maximum number of that, which is
the output a sequence?
yeah. I mean you are not so that's
Because I thought you were getting the 3D structure.
well, you're getting the 3D structure based on the information that you're outputting, which is the distance from each distance of each amino acids in relevance in relation to another amino acids, as well as the angles.
That's all gone.
So that's how you are representing the. There's more. that's how you're representing the 3D structures, right? It's not that, oh, this amino acids is in this space
Yeah.
of whatever. So yeah, sorry that I didn't make that clear. That's how you represent the data. So yes.
Can I have the last one?
It's asymmetric.
Yeah, I think I should have, give out an
No,
example.
metric.
Anyway. So,
Metric's
yes.
got those things.
So, great question, by the way.
Great question.
That we figured this
Great
out.
question. Let's analyze this together.
No, but seriously,
Rocket
doesn't
ship.
do that.
Rocket ship emoji.
That always pisses me off about
I'm
GPT.
gonna start putting this in my slides. Great question, and nobody will ask anything. Put a check mark.
Okay, and now we are going to talk about how Google did this, right? So basically, what we have is 4 parts of this. The algorithm consists of 4 parts. The first part is basically take the sequence and then processing the sequence for our ResNet to derive a attention. I shouldn't say attention. It's a distance map. That's what it is, basically. And then it's going to go through another sequence that actually, based on the embedded distances for each amino acids, predict the actual structures, and finally several tricks of gradient descent and the random restart for the final output of the model. And this is the structure of the ResNet. I may come back to this slide depending on which one is better. Okay, so should I go into it right now? No. Okay. So first of all, the data. Where the data was extracted from is the data bank, and oh geez, these. This is a PDB. This guy I forgot. the names is a little bit, but anyway. Oh yeah, UniProt I think. So basically, protein data bank will give you the structures of every single protein known to man now by this point anyway. So yeah, what the structure represents is just the what we discussed earlier, the angles, the distances of each amino acids in relation to each other, and then the sequences, which is how do you combine these amino acids together to form all the proteins. And in the processing of the data, so the processing of the data happens in this stage. The sequencing, and then the MSA stands for, it's been a long day, guys. Oh God, hold on, I literally had it. Dun, 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 dun.
Just twist it. Say something with twisting.
Seems likely.
I'm
Something to do with twisty.
Is that true, Jared?
5, 4, 3,
You write me down.
2.
Wrong, that's not true, Jared. Yeah.
Multiple sequence alignment, yes, multiple sequence alignment. I'll get to what multiple sequence alignment is, or how do you think of it in a minute, but I kind of just want you to kind of go through the basics of this. So basically we are taking, you know what, let me just explain it right now. Multiple sequence alignments, which was better represented in the AlphaFold 2 paper, which is kind of silly. But I guess AlphaFold 2 is the one that is really more impactful, and I guess Google didn't even bother to write a good paper for AlphaFold 1.
Sure.
Anyway, multiple sequence alignment. Basically, you can think of any amino acid that is persistent in nature. let's say hemoglobin. Do we know what a hemoglobin is?
Nope.
Is that what makes your blood red?
Yes. And then what's the functionality of it?
It makes your blood
Yes, your blood is red. It's very detrimental for your survival.
The oxygen.
Yeah,
Binds to
exactly.
oxygen something.
Right, so hemoglobin is the reason why your blood can carry oxygen. Right.
And white's red.
And white's right, exactly.
More importantly.
Yeah, so the interesting part of hemoglobin is that hemoglobin in a human is the same hemoglobin in a fish or in a rabbit or in a
Chicken.
yeah. I was thinking about a different word here.
Go ahead and say it.
So what is important about this this consistency of amino acid is that when we try to derive find correlations between different amino acids, there exists this relation where you take apart part of the amino acids, like theoretically, other parts will start to begin to change as well, because your amino acids and different parts of that amino acids have different charges, and that different charges will make the structure either stable or unstable, but it will eventually collapse to a stable state depending on its what it's binding with, what elements it's binding with, and that's quite frankly a chemical reaction. But that's but the point of the multiple sequence alignment is to try to find that correlation, right? Trying to find, are there different amino acids that correlates with different kinds of amino acids, and now that is somewhat similar to attention, because when we think when you think about these amino acids as in each one of them as an embedding, then all of a sudden you have the possibility of one amino acids have a like similar persistence or electric charge with another amino acids, and there are chances that they coexist all at the same time, or they're close to each other, they're distant of each other, they're always of a particular angle. So the point of deriving this sequence, the attention out of this sequence, is that we can find potential patterns in between our amino acids.
Yeah, this is like the template lookup where you find similar amino acids and give it to help it out, right?
Basically, yes. Exactly. So in AlphaFold 2 is when the MSA gives the templates. AlphaFold 1, I'll go through AlphaFold 1 first, because AlphaFold 1 is basically just one little part of AlphaFold 2, which is pretty cool.
Are they both are they like both published? You said like AlphaFold 1 isn't published?
Oh no, it's published.
It's published.
No, I'm just saying when Google published it, like
It was like after they'd already.
yeah, AlphaFold was published in 2020, and then AlphaFold 2 2019, and AlphaFold 2 is 2021.
I hate that
What
one.
about paper?
Really?
It's hard to read.
2020.
One
It's
chemistry?
in
23.
nature, and two
Is there
is like
before you?
AlphaFold
Not
2
yet.
and 3 are
I doubt there will be one soon,
AlphaFold 2 and 3 are what you want.
because they
AlphaFold
kind
2
of
and 3, there's a
just
3.
dump all their work
Yeah.
already, and to our knowledge, they're not working
I was just
currently
wondering
on
if it
something
was-
that's
it's in nature.
fundamentally new.
Just like Apple.
Is that
Just like
feature
Apple.
papers?
Anyway.
Is that well known?
From my experience, because I don't know how to read nature paper.
Yeah, same phone every year.
Talk to
So okay, all right. Go back to our data. So our data is is processed with this P matrix. So basically, this P matrix will somewhat define the distances between each residues. I need to start calling it that, residue. I'm bad with terms. Between each residues in the amino acids sequence, right? Because so that's what MSA is doing. We're deriving the correlations between residues. So think about this as this is a residue, this is a residue, and this is a residue. These residues will be processed with its distance with Pij and D. So that's a matrix. And then also we will calculate for every pair in every region of the distance matrix, which we'll get to in a minute. This is just a probability, by the way. This is what we're deriving in the first part. The distance given the sequence and the MSA of that same sequence. And then the next one is the two angles. The angles given the sequence and then the MSA of the sequence for every IJ pair as well. Sequence features. This is the positional information here.
So you want to predict it?
I'm sorry?
Is that what you want to predict?
Well, yeah. I mean, let's see. What you want to predict is the sequence. This sequence is your training, what you're training on essentially. So we derive this P for our process data so that basically we embed this data. And I'll talk about how training goes later. Sequenceless features, this is where I'm just totally lost. Because, okay, oh god, there's like, I don't know, like 200, like almost 200 features here. But then you will be crazy to think I will figure out what is one hot amino acid type and the PSI blast and H
You don't know
blitz
Bliss
profile overnight. But no, I wonder if that's why I wonder if my lab partners who is a chemistry major will know this. Maybe, yeah. He's like, yeah, you stupid computer science major who never go outside. Okay, so basically what the resonance is basically scale down into a CNN and then scale up again. That's the resonance. The point of having this resonance is basically because, well, this is very large sequence, right? This is, how large would this be actually? Well, that depends on your INJ. But yes, so for LL, 60 by 64 region.
Quadratic with respect to the.
Yeah, L times L covariation features. So, length times length. So basically every single residue in the relation of another residue, and then this whole embedding is like 128 deep. And the 128 comes from all of this and the sequence length features. Does that make sense?
Yeah.
So what we do here is batch norm. Why the face?
Back in my day. You know at the times, use RMS norm.
Take the batch norm, you reduce that to a 60 by 64 residual block, convolution block. Well, convolution because this is a very large embedding and you have limited computation power. And I think this can work pretty well, assuming that proteins that are closer to each other, residuals that are closer to each other are more relevant to the data. So the global attention that is like outside of the attention shouldn't make that much difference. But that's just a theory. That's what I think why CNN works. Just this itself works better than other competitors in CASP.
L is your sequence, right?
I'm sorry?
L is your sequence.
Sequence length.
And I'm guessing you order that based off your
Yeah, by sequence. So for example, in here, like, the target, like T blah 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 whatever in CASP, the sequence length is L, which is 155.
And that has some ordering to it, so that makes sense.
Oh yeah.
That means it also has an ordering on the matrix.
I'm sorry?
That means it also has an ordering on the matrix. So the locality makes sense.
Yeah. And then what we have is the next part. So you scale it all the way down to 3 by 3 here actually, and then scale it back up to the residual convolution blocks, and then scale back up to this map. And then this looks like attention. This is essentially what the attention is the again, the residuals in certain amino acids correlating to other, to some extent. And then it will do the gradient descent for the protein specific potential, and then that's the rest of the training. What is the structure of this? I don't know. This is actually, I did not find this on the paper, which is again, it's like the first paper was just ass, to be honest. And Google have the bright idea that does every single bit of math just on in like math paragraphs. So if you want the math, if you want the equation of how it works, it's just embedded in there, but then you have to read all of that. So this may be the next thing that I go in the code and try to figure out where exactly the gradient descent is going.
Do they have that in 2 and 3?
I'm sorry?
They have gradient descent in 2 and 3. This step
What 2 and 3?
in AlphaFold 2 and 3.
Oh, no. This part is going to, like, this whole thing is going to show up in Alpha 2 again.
Okay.
Right, so which is why I'm going through this first. But basically, if you think about gradient descent, your goal is to out of your entire state space of this protein, you're trying to find the local minimum, local extrema, which will be the final representation of your protein. And there are a few things that it does. So gradient descent is to find to adjust the weight of your model to find the most optimal weight that will generate the final protein structure. And also it uses noisy restart just out of every single iteration of that gradient descent in order to reach a I guess to avoid it getting stuck in local extrema.
So is that gradient descent after you produce the map, or is it gradient descent to train the thing?
That is no. This is still.
Because it looks like
No, this is training.
this is training.
Yeah, this is not inference. This is like we are adjusting the weight on this guy, right? Sorry, not on this guy.
Oh, okay.
This is what we will get. We're adjusting the weight on these like two residual convolutional blocks, right?
And you do that via that gradient descent on the
Yeah.
protein specific potential.
Yeah, basically.
Oh, so that's probably just like something like optimizing the
I thought, is this it? Because I thought that was like another block.
Because it's weird that
That's-
they would put gradient descent there. It seems like they may be using that to fold the protein.
Yeah, distance and torsion distribution predictions. Is that just a loss function?
That's what I'm wondering. Is that the
Wait.
loss function, or are they using that to fold the protein during inference time? Because the graph.
Yeah,
shows-
I think. Oh right, yeah. This okay. Yeah, this is a literal folder then. This appears later. I'm pretty sure.
That's folding the protein.
Yeah, this is the folder.
That makes sense. Because you
Yeah.
look at the graph and you see how many steps it takes, and that folds the protein.
Right, but then that's also where the gradient descent comes in, right? So like it folds in a way that.
Well, it's just minimizing the. It's just minimizing the. I'm guessing it's just doing gradient descent.
It's just maximizing the TM score, I think.
Maybe.
No.
Probably not actually, because TM score is annoying to calculate. I'm guessing it just steps in the direction, like it just does normal MD,
You think so?
molecular dynamics.
Yeah, that is a great question. Here.
Because if that's a loss function, then that would be different. I don't know.
Yeah. And that's the. I'm pretty new to reading paper too. I'm still trying to learn like.
Well, each step of gradient descent greatly
What are
lowers the
things?
potential.
Loss. Cross entropy. Yeah, I read it. Cross entropy loss. Of
So it's
wait.
minimizing
Auxiliary
the
loss.
categorical.
Trained with stochastic. Yeah, okay, yeah. Ugh, God, it's like in the very back of the session of the paper. It says like the network is trained with stochastic gradient descent using a cross entropy loss. The
Oh.
target is a quantification of the distance between the C beta atoms of the residuals or C alpha for glycine. We divide the range 2 to 20 to is that alpha into 64 equal bins. Then the input to the network consists of a two-dimensional array of features, which features each ij, which we talk about it later.
Yeah,
Earlier.
it's just for the deep neural network.
Yeah. Okay.
The gradient descent step here, I think, is to fold the protein.
Yeah.
And that's different.
Oh God.
I think they use. I am thinking they're using gradient descent to fold it after they predicted all the residues.
That's so messy. Yeah, because
As long as you
nowhere,
have the residues, you can
nowhere
do it.
ever does it like. I think maybe that's something that's just persistent in the literature, and I'm not familiar with the folding
I think
part.
That's just normal molecular dynamics.
Yeah, I think maybe that's what it is, and which is why I'm so
Which is why
lost.
it's not in the paper.
Yeah, it does mention like auxiliary loss, metric, like the.
Let's search out, let's see gradient descent for, you're saying that first time?
Yeah.
Like the last gradient descent.
Well, I know, like, it looks like that's how you would normally simulate a molecule.
But that's
By
just
just
not
following
even.
the directions of the residue.
But
or the-
what
or
is
the
this?
potential.
Oh, the frame align point error. Is this gonna give me what I want?
Dr. Tao's pretty cool.
Yeah,
Real.
I
Is
haven't.
doing
I haven't
stuff with
talked
Dr.
to
Krakow.
this.
He's a crack.
Dr. Krakow. She's
Oh.
German. It's like a
In
German.
the case of AlphaFold,
And we're doing like molecular property prediction.
frame align.
Yeah. So it's not like AlphaFold where you're trying to find like the 3D configuration. Rather, you're trying to like predict properties of the molecule or metabolism and shit like that.
Error.
Just GNN stuff, graph neural networks.
Yeah, I literally. I don't know.
I don't know anything about AlphaFold. So.
I actually don't know what, cause like.
Maybe look at it later.
Yeah,
Some
I'm gonna.
way to fold it.
I'm gonna skip this step. Skip.
It looks like it's just folding.
Yeah, it does fold, but
It's folded.
good question. Like, what's the loss function? I read it was rate entropy. I guess I
I
just.
think that's
cross
true deep
entropy.
neural network.
Yeah, but yeah, exactly. But
Like the
nowhere
cross
else
entropy
in
stuff
here
is
that
trained
they
in network.
discuss where it
That
like
gradient
what is
descent
it.
is something else.
Yeah, I think cross entropy is trained the neural network, and then you have the second gradient descent part, like
Yeah,
which
They're
does
using
this
that as a
also.
heuristic.
maybe that's.
Well,
That's what
it's
it sounds
like gradient descent is just minimizing a configure. It's minimizing something, and you use a configuration for that. And in this case, I think it's basically maximizing like how good the molecule is. Like you start off with that structure there, which is like physically bad, and if you perform gradient descent to maximize how good it is, which I guess is using the potentials. Like if you have a bunch of forces pushing on things, then you could step in the direction that minimize the forces.
Like stabilize.
Yeah, to stabilize.
Yeah, I guess that makes sense.
That's what I'm thinking.
Yeah.
But I don't know.
How did you get to that conclusion though? Is there something in that chart?
Well, they have the chart there, and then they show gradient descent talking about that. So, and they show the gradient descent steps below it.
What you're saying makes sense though. Like
That's what I'm thinking.
finding the equilibrium.
Yeah,
Yeah.
because in the end, that's what you want to do, and it looks like it's predicting like the residue.
Because
So
like
the neural network is just predicting the torsion, like the
Yeah.
angles and the distances, and the gradient descent's doing all the.
It's doing the folding.
That's
Yeah, that's for sure.
clever.
Yeah.
Do you have to use gradient descent for that? Can
Well,
you
it's-
use?
You can use normal MD, but
Yeah.
gradient descent, I guess, is better. It's definitely a lot better than normal MD.
Gradient descent.
Gradient
Hill
descent.
climbing.
Yeah. It's easier.
Well, like, like normally, if you did MD, you would have to simulate, like, using super small step sizes. You know, take a supercomputer and do that. I guess in this case, you don't have to. Because you have the potentials, which I guess.
I have no idea. I'm gonna have to like I'm gonna end up reading that paper.
Yeah. Don't read AlphaFold. Read AlphaFold first.
30.
So is this for like drug discovery or something? Like, is that the reason? These proteins? We just like to push them around. I mean, usually it's for drug discovery,
It is, yeah.
but you can do it for a lot of things.
You can also just do it for fun.
Yeah.
Recreational drugs?
Yeah.
Yeah, recreational drugs. You're like, man, I want to pull a protein.
All the three colors.
Yeah. Well, there's also like ligand binding, which is drug discovery as well, but that's not this.
Like in our lab meetings, like our chemistry post-op will say a bunch of stuff, and then Eli like looks at me and he'll like explain it in CS terms, and I'm just like, alright, cool.
Thanks.
Okay, I literally reread the structure realization by gradient descent. Nowhere says loss. It just talks about torsion angles.
The sticker.
Oh, you never saw
The
this?
incel sticker.
Yeah.
It says incel.
All right. Okay.
It's true.
No, it literally doesn't tell me what loss it is. It literally is not in the paper. I thought I was crazy.
So what we're thinking it is so you have like just look at the green part.
Yeah.
The green part is cross entropy.
Yeah.
Now we have a fully trained neural network.
Yeah.
Now we're not looking at this thing at all. Now we're using this thing for inference.
We're using this.
Yeah, so then you take that
To
and
realization,
look at the
right?
leftmost diagram, the leftmost protein pointing at 0. That's what you start with, but
Yeah.
you know the angles and the residues.
Yeah, exactly.
And then what you do is you step into, so you have a bunch of forces acting on that because of how the protein exists,
Yes.
and you want to minimize or maximize how good it is and minimize basically the force interactions.
Is
so
it
that
just
the-
maximizing TM score and then minimizing RMSD?
No, because I doubt it's maximizing TM score because
Okay.
that's just a metric that you're looking at.
Right, yeah,
It's-
that's just
I mean,
accurate.
it says it right there. It's basically, it greatly lowers the potential. So it's like making it stable. So you have this protein, there's a bunch of forces acting on it, and you just step in the direction to make it in a stable
Yeah.
state.
No, I think that's spot on. That's 100% what it is.
I think, yeah, that's what we think. That's our conclusion on this side of the table.
Wait, so what is it that is minimizing?
It's minimizing. It says it's minimizing the potential, so it's just putting it in a stable state.
Just
Yeah.
just the potential.
I mean, you can look at it. If
Okay.
if you had, let's say I had a value that said how stable this was,
Right.
you would want to maximize that.
Okay. Yeah.
And if you look at the diagram, like TM score doesn't matter. TM score is just like
Mhm.
TM score is a way to evaluate.
Yeah. Yeah.
But look left to right, and let's say from left to right there is a score I am increasing,
Mhm.
which is the stabilization. And you can see as I increase the stabilization by moving around the protein itself,
Right. Yeah.
it
It's
goes
like
into a stable
folding.
state.
Yeah. There's like different steps that it's doing
Yeah.
to fold.
So you're basically you're performing gradient descent by moving the either atoms. You're moving something.
I'm moving the residue.
Oh, so you're moving the residues
Mm.
by a gradient descent
Yeah.
to put it in a stable state.
Okay.
So as you can see on the right, it's in a pretty damn stable state.
I think I can't explain what potential is yet. I think that's my.
I think
where I'm
potential
not
is literally
understanding.
like energy,
Like the inverse of stability, or
or sure.
whatever.
Yeah. But
Intuitively, I mean, all
How
gradient
do
descent is
you-
a search, but intuitively, in this case, it is very much just. a
so I guess you're just
search for-
minimizing the
First.
RMSD of potential.
No,
No, it's not.
you're minimizing something.
Well, you're minimizing the potential.
Root
Yeah.
mean squared.
No, you're minimizing the potential.
Those are the metrics.
Oh yeah, I guess you are minimizing RMSD, which is
Root mean square deviation.
sure.
What?
Sure, root mean square deviation of potential.
I guess, but like that's not mentioned in there. You know what I mean? So like I don't know.
No,
this
I
is
think-
just a graph.
Yeah, that's what we think. is-
1,200 steps is like not. I feel like.
No, not bad for like
Yeah, I don't have any reference for this, but I feel like it's not bad.
for this. Yeah, and that's kind of the benefit of predicting protein structures instead of simulating.
Yeah, because if you simulated, you would have to have a supercomputer, and it like there was this one thing we simulated. It was like super small, and it took like a whole day, and they were super excited about it. They're like, dude, this thing's crazy. And it was like a 1 second clip.
Yeah. So
it was hilarious.
the oh yeah, so basically what we'll get to this again, but basically what we're trying to get here is the residue to residue relation here, right? We'll get to that again, so that's why I want to mention that once again. This is a ResNet. It uses ELU because the negative are not like they are negatives, so
Why you?
I have no clue. Well, think about it.
Mimics your brain.
It's like allowing negatives, right? And it's like scaling the negatives.
It's
And-
basically ReLU but down by 1.
Yeah, exactly. So like you allow negatives here, which presents, I think
It's probably just an arbitrary choice they had that work.
I think maybe.
Who was thinking?
Anyway.
Yeah, it was actually hinted.
But
It's only
I promise you, like if you try to do anything else, it probably wouldn't work as well.
It probably just worked, ELU.
You know.
Yeah.
Yeah.
Like
So
you could probably throw like a swag glue at it and it worked better. Yeah.
That's like pre-swag glue,
Yeah.
right?
Swag glue was like 23 or something.
Yeah.
mhm. Yeah. So we can see that.
It's a swish. Sorry, Jerry, go ahead.
Yeah, so this is what the attention is. You can't really see it, but here you can see the little like distance. So like from this node, let's say, to the distance from everybody else is this line. Essentially, that's what this attention is technically doing.
That's pretty hot.
Yeah.
I'm a fan.
Well, the limitation of this is that we derive this distance from our like finding finding the relations between the different residues, right? So we're assuming that the logic behind this is that the distances of this of a residue to the rest of every other residue is directly correlated to our metrics here, which is which I think is the kind of the assumption all along for computational chemistry, but that's when the Google engineers realized, yeah, that assumption and that convolutional neural network ResNet is somewhat limited. So here introduces EvolFormer, end-to-end transformer. It's two transformers that talk to each other. I'll get to that. And it achieved a median backbone of the RMSD of 0.96, not percent. A is like the it's a specific term on here, right? That is like the kind of the loss.
It's a score and it's good.
Yeah, the score of the like the distances, I think, of the node to everybody else.
0.1 nanometers.
0.1 nanometers.
Whatever.
Oh, so that's
Yeah,
That's
okay.
That's the error.
So like that's
Wait, that's
AlphaFold right here.
0.96. That's crazy.
that's about a third of everybody else.
Wow.
So yeah, so and yeah, they eventually right here. So they received like for this case they received the TM score of 0.93 and this one 0.96, and this is a pretty complex protein if you ask me.
Look at that.
And basically when the Google engineers could achieve 0.96 with their model, that was the moment that they won the Nobel Prize, because they solved the problem of computational protein structures.
That right one's insane.
Yeah, this one's big. Look at this guy.
Would they solve it?
Yeah. No, they solved it because this is out of this is out of AlphaFold 2. This is what AlphaFold 2 got based on the original sequence. Just behold it for a second.
Getting
Solve it.
anywhere close to that for the right one is crazy.
Yeah. So I'll stop trying to describe it and just go into how it works. MSA we just discussed.
What's
Right.
that?
Get real. MSA is our residue relations among other protein structures, among other amino acids, and now we have templates. What templates is actually just positions. This is the actual positions between different residues. So if you can see like, oh, there are different residues, and then we have a combination of both residues here, and then that will give you a distance score here. And this pictures from Veritasium, who is awesome. Veritasium is basically Mark Rober, but actually good. So check it out.
Mark what?
Mark Rober.
Mark Rober?
Yeah.
Oh, the YouTuber?
Yeah.
Okay.
Veritasium.
I heard Wahlberg. I was like,
Sorry.
Did he make a video on this? I know this is 3.
This is Veritasium, yeah.
I don't know. Maybe.
Very good video. Anyway,
oh, it's a
so
watermark.
Oh yeah.
so what Veritasium described the our MSA is basically a biology tower. So basically, how does different amino acids correlate to each other? And then the template is the geometry tower. So basically, the geometry of this of our amino acid sequence. So instead of like AlphaFold 1, we're using the biology tower to predict the geometry tower. We'll deal with geometry here because why we need this information to derive actual distance. We can just do the actual distance. But of course this this relation between different different amino acids in its with its residue is still important, as again explained before. Different but very similar amino acids have a tendency to act a certain way when certain residue is taken away or reacted with. So here we are is the architecture of Alpha 2, aka EvilFormer. EvilFormer is actually just this one block, but whatever, how Google wants to name things. So basically, yeah, so we're still using the same data from the data bank and then the protein sequence. And what we are trying to do here is basically run the data through MSA and the positional templates, basically at the same time. Pairing is this. Pairing, I'll get to it later, it's called triangular attention, but I'll get to pairing in a minute. So basically we derive these two, let's say, attentions, basically distance of different residues and different amino acid chains. And we are here to, and these are what that is, right? This is still just, this is basically alpha 1, still the same convolutional blocks. And we will get this MSA representation and the paired representation as the result of these two data processing.
Is MSA updated in the attention box?
I'm sorry?
Is MSA updated in the attention box? Because obviously pairs are, but is MSA?
Oh, MSA, yeah, MSA is still up. So okay.
You need to update that.
Yeah, because so now think about like we have these two. Both these two will be updated.
Yeah, but why do you need to update the MSA?
I'm sorry?
Why would you need to update the MSA?
Oh no, you're training these two at the same time.
Ah.
You're training these two at the same time, and that's where it's interesting is the structure of EvilFormer. EvilFormer has a mechanism of communicating between these two.
I guess it's similar to Stable Diffusion 3 where you have text, the text and image streams.
Okay. I'll have to read that again.
Yeah, I mean, it's basically of the two streams. It's just less complicated than this.
Yeah. So that's the representations of the MSA attention and then the template. This is the MSA attention. I mean, it's just attention. It's like the same as I don't know, text attention. And here's something interesting that is called triangular updates, but I'll get to that later. Let's talk about the structure first of the 48 blocks EvilFormer. And 48 blocks means like it will run this 48 times. So what MSA does is get the representation and then when it finds, it will give its found sequences and high attentions transit to pair representation, and pair representation gets that and do the triangular pair triangular attention to adjust its weight, and then it will go back to MSA again, do this again, do this again. This is the same thing, by the way. It's just the updated version of this, time-wise. So okay, what is triangular attention? Well, let's first discuss the geometry of a triangle. So if I have a triangle of, can I write here? I'm gonna use this. Is it? There's no way. It's not touch screen. You lied to me. Jeez. Okay, sorry, I see my mouse now.
Click the pencil.
Yeah, it's a long way here. Okay, yeah, no, this is lagging so hard. I can do it here. All right, so let's say we have a triangle, right? Of side A, B, and C. So what do we know? Like, if we know about A and B, what do we know about C?
Nothing.
The length of C
Nothing.
It exists.
is smaller than the sum of A and B. So in any
It's not a right triangle.
what?
It's a right triangle.
What's a right triangle?
Where's the 90-degree angle?
This is not 90 degrees. Anyway,
Read up. If you know the angle, you can find the distance.
true, but that's
A plus B is less than.
it's not that it doesn't concern about angles, but basically it concerns of the fact that the third length of the triangle the third side of the triangle will not be greater than the length of it will not be greater than the length of the previous two.
Can you prove that real quick?
Prove it's
Well,
not.
yes. So let's assume that we have a 180 degree. We have 180 degrees here. You got me started. If you have 180 degrees at angle AB, angle AC and angle BC will be 0, and in that case C equals to AB, right? But then the moment you change the angle to below 180, then that's when C will be
Actually, yeah, I think you can prove it with Pythagorean theorem.
Yeah,
Just divide us by
exactly.
that.
Anyway.
Yeah.
So yeah, exactly. You got the point. Let's say so that's why it's important, right? Why this theorem, why this theorem is important is, let's say in our pair representation, I have three. Let's just find three random residues, I, J, and K, and I have a value for I, J, I, K. Ji, Ki, Kj, and Jk, and we can plot this edges in this graph. This is the relations of it. So what we can conclude is that our Ij plus Ki will be greater than Jk, and then given this knowledge and this relation, we'll see that we can update these edges based on what we have adjusted in other edges. So this is somewhat like a sanity check to make sure in this triangular pair, no C is greater than A plus B.
This is basically just forming triplet relations instead of pairwise.
Which they call triangular attention. Do you guys like the name triangular
No.
attention?
Triplet attention I've heard of, I think.
Well, it's just creating three-way. Well, they're doing it in a smart way because you could do a volume where you have three.
Yeah,
volume
3-dimensional, but that's
Yeah.
disgusting.
And also that requires n cubed space.
Yeah,
While
space
here,
and computation.
they're doing a smart method where you look at since you know it's bounded, you can kind of approximate it, I guess.
It's kind of just like a sanity check, which it doesn't like. It just like let's say the updates of different cases of updates. Like it doesn't determine the other case. Like you can literally see right here, like k and ik literally have different values.
Yeah.
But it kind of
They're just forming triplet relation.
yes, exactly, and that's its that's its triangular attention here.
Yeah. I hate that.
So I guess that's important because let's say you have 3 residues, and that 3 residues, because the previous one we only AlphaFold 1 we only talked about the relations between 2 residues, but now we add the triangular attention, and then we can concern about another residue here in quadratic space.
We also need 3 residues to form an angle.
Yeah,
If you only have 2, you only form
there's
one.
there's only
Or you only form
So basically you can update based on our triangular attention value to update some of the incoming or outgoing edges. And after I found this really cool thing. After our eval former. So what it does is that it's going to run this 48 times, structure 8 times, and then recycle back to the eval former. And that's the cycle of AlphaFold 2. So the 48 blocks, it will run this 48 times, adjust the pure representation and then the MSA representation. This structure module, now it says it, right? Like what folds the protein. So the structure module folds the protein 8 times, and then you'll feed it back 3 times here again. Okay, the reason why it recycles 3 times again is because there are parts of the protein that has low confidence.
Okay.
And you feed it back again to find the to refine the attention for I guess for those low confidence areas.
Makes sense.
And that gives that is the entire structure of AlphaFold 2.
Nice.
Good job.
Any questions here? No? Okay. So yeah, well, AlphaFold 3. I won't time reason I won't get to everything, but basically, as you can see, they did do some they did do some different data. I think they added a genetic data with what are the 3 anyway 4 whatever. But what it does differently is the embedding part. Instead of just the MSA and then the pair, it gives the input. It embeds it into inputs, pair, and single. So we didn't have inputs here before, right? And the inputs just kind of guides it through the entire process.
It's like stable diffusion. I'm guessing that guides the statistics. It's
This is literally stable diffusion.
No, not that.
I mean, not stable.
The inputs, I'm guessing the inputs are an add-in module.
Yeah.
An adaptive layer.
Yeah. I mean, parents.
It's basically stable diffusion.
Yeah, it's basically so what it does then is builds the template module, which we talked about earlier, the biology tower, geometry tower, MSA, the biology tower, and 2 times here, 4 times here. I don't know why they determined the times. 48 blocks for the pair former instead of the eval former this time. So yeah, we feed it back 48 times. And then we have, instead of the structure we had earlier. So this is still very similar, right, to AlphaFold 2. But instead of doing the structure module that just folds it, which I need to figure out what the structural module is. That's the part I haven't gotten into. We use a diffusion module, and this diffusion module will.
That part's cool to me. You basically have so before we were using gradient descent.
Yes.
Here we're using a diffusion model.
Yeah.
to model it.
instead of gradient descent. So the benefit of diffusion, of course, is that you're just running it through it once it's linear. You do not have a quadratic computation for your inference or training. So then this is a lot cheaper. It's a lot cheaper. The problem with AlphaFold 3 is that its accuracy, I think, is not really good. I think it's only like gets an average FM of like 0.5.
Is it worse than 2?
It's I'm pretty sure it's worse than 2.
They're harder.
But the
I think 2 did. Oh, 2 did.
two is the one that won the Nobel Prize. But the novelty of AlphaFold 3 prompts the future question: is that can we use something computationally cheaper to evaluate protein structures, and will that lead to more innovations in computational chemistry that will help us to discover more polymer structures or discover more general rules and applications in medical and biological labs?
I'm guessing it's less because of the diffusion model. 'Cause
Yeah.
The diffusion model is inherently a probabilistic model, increasing the probability of a likely sample.
Yeah, exactly.
While your gradient descent method is not probabilistic.
Yeah, because you're taking the derivative and you're traversing it.
Yeah. Like you may end up with multiple local minima, but technically those are equivalent in terms of how good they are. Here
Yeah.
you have a probabilistic model, so
Yeah.
it makes sense that it would be worse.
Okay.
In my
Because diffusion, you just have like the space.
well, you can think of it as one either following a trajectory
Yeah.
and then going along some flow, but equivalently, you can think of it as maximizing the score. And score is a metric of basically like if I give a classifier an image
Yeah.
and I say how good is this image,
Okay.
the score is the log of that probability.
Yeah.
Or
That's
the
diffusion.
derivative of the log of that.
Yeah.
So what you're doing is you're following the score. So essentially what you're doing is you're either following the flow or just as like you can change the derivation, it's the same derivation, you're increasing the probability.
Okay.
So you either follow the flow or you can say I'm increasing the probability of this sample to be good.
Yeah.
So like you can think of if I'm generating a picture of a cat, I give it some noise, which is like 0%.
Yeah.
But the model is telling me where to move to increase the probability of the cat. Here it's the same thing.
Yeah.
I have garbage and it increases the probability but guided by the other part.
Yeah. That makes sense.
So that makes sense why it's worse, because it's a probabilistic model.
Yeah.
But it's an interesting direction.
Right. But because everything here is the same, right? And
That,
then
yeah, that
some-
part's the same. Like I'm
Yeah.
guessing if you use that and you use gradient descent, it would do just as good. But it's a diffusion model that I think makes it worse
Yeah. Okay. Interesting.
because it's probabilistic.
Yeah.
Like if I give it a different seed, it's going to produce a different output.
Right.
Which
Not by a lot, right? You
it
could
shouldn't be. It depends on what your output space looks like, and
Yeah,
that's
but also it's probabilistic, right? I mean, of course, there's always a maximum probability, but then the point of having different temperatures that you will use some of the lower probability
another thing.
actions
Yeah.
instead.
Well, another thing is also this doesn't have to follow the condition you're giving it, while the other thing I think has to be physically accurate because
Right.
you are you're basically following you're following the potential,
Yeah, right.
which has to be physically accurate. While here it doesn't have to be physically accurate at all. Yeah, it can be physically accurate, but it doesn't have to be. There's nothing.
That's kind of cool, I think.
I think it's just a problem with diffusion models. Because you're conditioning it, but the conditioning here is a soft condition. It's just like with text. If the model wants to follow the text, it can, but it doesn't have to.
Right.
It's just better if it does, but it doesn't have to. So diffusion models are kind of okay at following text.
Right.
Same thing here. It doesn't have to follow the physical guidelines of the world, but it can, because you're giving it that information.
Well,
Do you still use gradient descent though? Like you can, right?
No, I mean, you're performing a kind of gradient descent by stepping, by maximizing the likelihood of your output.
An output, but like.
But your diffusion model's predicting the direction. Like, you can think of, a gradient descent is just following, it's just following.
Well, yeah, your space. And
That's the same thing, except instead of following the derivative, you're following the output of your diffusion
the,
model.
the probability of.
Well, you're just it's just the output of your diffusion model, which is either velocity or it's the score, and the score is the derivative of your probability telling you how to maximize it.
Okay.
How do you increase the probability? One or the other.
Good stuff.
Interesting. Yeah, so that's the current limitation of AlphaFold 3. And to conclude, AlphaFold 1 demonstrated. I'm gonna wing it. AlphaFold 1 gives us MSA, but in the pursuit of trying to predict template from MSA, gives it trouble to completely solve the problem. So the next year, CASP 14, Google decides to still keep MSA, but also remains is the template added with triangular attention to adjust the weight of the template, and therefore forming the Evo former that will engage the two different attentions so that it will adjust somewhat together, and finally forming the what we know as AlphaFold that solve the problem of our protein structure prediction. I guess AlphaFold 1 published in 2020, they submitted in 19 anyway. And then AlphaFold 3 is still a very front edge, very innovative model, so that which that it uses the framework that made AlphaFold 2 so good with diffusion model, and that is the current big question in current literature of computation, biology, and chemistry.
Nice.
Thanks so much.
You're welcome.
So
All right.
this is like my first time doing this